Okay, so in the previous video we were talking about example exercise number 2. First we calculated the mean of the first n natural numbers, and that was basically n plus 1 divided by 2. And then we wanted to calculate the variance of the first n natural numbers. And so you know that the variance of sigma squared is equal to 1 over n sigma of f of I times x of I minus x bar whole squared as I goes from 1 to n. So we calculated basically x bar to be n plus 1 divided by 2. So you can write that as sigma squared is equal to 1 over n times sigma of x of I. And we said that basically f of I, of course, was equal to 1 in the case of this data because well, the data doesn't repeat itself, and so you can f of I is in all cases is equal to 1, so you can just simply write it as sigma x of I minus x bar, and then you can write it as 1 over n times sigma of x of I minus x plus 1 divided by 2 whole squared. And then you can write it as 1 over n times sigma of, basically this is then a minus b whole squared, which is equal to a squared minus 2ab plus b squared. So now this is a squared, this is b squared, and this is minus 2 times a times b, which is x plus 1 divided by 2. So you can cancel these two out. And then you have basically negative x of I times x plus 1. And so the next step is to basically you can write this as 1 over n times sigma of x squared plus basically sigma of x plus 1 whole squared divided by 4 minus sigma of x of I times x plus 1. And of course there was something that now over here what we have, we need to make some changes here. And the changes are that our variable is not okay, so now our variable here, basically you can imagine that all of these numbers 1, 2, 3, 4 and so on and so forth, that these are basically you can call them x of I, right? And you can call them x of I, and your formula is 1 divided by n sigma x of I minus x minus, and that is n plus 1, that is n plus 1 divided by 2, and this n refers to then this n refers to basically you see over here, when we have these numbers over here, this n refers to the number of these terms that we take here, meaning that okay, so now basically this n over here, this refers to the number of basically terms that you take, and then based on that you will get some number in this expression, and that is the mean of the first, for example, n natural numbers. Now in this formula you can think of this n as the lowercase n as well, and of course then x bar would be this value here, n plus 1 divided by 2, and you have to keep x of y as x of y. You don't need to touch that, but then I will write this expression as basically 1 over n, lowercase n, you cannot mix everything up, so lowercase n, and sigma, then f of I, of course I want to get rid of f of I and just write this as x of I minus x bar whole squared as I goes from 1 to n. And so sigma squared is equal to 1 over n times sigma of basically x of I minus n plus 1 divided by 2 whole squared as I goes from 1 to n. And okay, so what happens is that you can simplify this, meaning that you can write this as sigma squared is equal to basically 1 over n times 1 over n times basically sigma of let me write it as, for example, sigma of, and this is a minus b times raised to the second power, a minus b to the second power, which is a squared plus b squared minus 2ab. So you can write that as basically sigma of, for example, a squared would be x of I squared, b squared would be n plus 1 whole squared divided by 4, and negative 2 times a times b would be negative 2 times x of I times n plus 1 divided by 2, and these two you can cancel out. You'll get negative x times n plus 1, negative x of I, of course, negative x of I times n plus 1. negative x of I times n plus 1. And then what you have is basically this expression, which you can write as basically sigma squared is equal to 1 over n times 1 over n times sigma of, or let me write it this way, 1 over n times sigma of x of I squared as I goes from 1 to n. And then over here you have sigma of n plus 1 whole square divided by 4. You can write it this way, n plus 1 times the whole raised to the power 2 divided by 4. And you can write this 4, you can take it out, write it this way, so then you don't have to write this anymore. And then you have sigma of x of I times n plus 1, negative sigma of x of I times n plus 1 as I goes from, for example, 1 to n. But then you can, since this is a constant multiplied by this, by x of I, you can take it out, write it as n plus 1 times sigma of x of I as I goes from 1 to n. So you can write this way, meaning that I can write it as n plus 1 times sigma of x of I as I goes from 1 to n. And of course you can see that over here, for example, you don't have anything that all of these basically terms I is equal to y to n, or I is equal to I goes from 1 to n. So over here you don't have any you don't have anything dependent upon I, so you can just take this out. You can just take this out and write it as, for example, n plus 1 whole raised to the power 2 times sigma, basically 1, sigma of 1 when I goes from 1 to 0. So this is going to just be equal to 1. So then you can simply write this as n plus 1 whole raised to the power 2 divided by 4. This part over here you can write as n plus 1 raised to the power 2 divided by 4, for example. So that is basically that. Now, one thing that we need to take care of here is this thing over here, which is sigma x of I squared. Sigma of x of I squared when I goes from 1 to n, that you need to calculate. Then you need to calculate sigma x of I when I goes from 1 to n, and then we'll get everything in terms of n, and then we can simplify this thing. And as you can see, this sigma notation, it simplifies everything very, I mean, in a great, in many basically different great ways, which, of course, I mean, without sigma, you would have to just keep writing and writing and writing, and everything would be so confusing, at least. Okay, so now in order to calculate these two things, what you need to do is basically, for example, if you want to calculate sigma x of I squared as I goes from 1 to n, what that means is that you have x of I squared, meaning that I starts from 1 goes all the way up to n, so you have x of I, meaning that basically you start with x of 1 squared, and then you add to that, because you have the sigma notation, you add to that basically, then I becomes 2, so x of 2 squared plus x of 3 squared plus x of 4 squared, right, plus all the way up to x of n squared. So since we're talking about the set of natural numbers, x of 1 in the set of natural numbers is, of course, starts with 1. So this would be equal to 1 squared plus 2 squared plus 3 squared plus all the way up to n squared. So that's why we write this as sigma x of I squared as I goes from 1 to n. And I don't know if we have talked about this. So now if you want to add these terms together, these are the sum of the first basically squares. And the way that you can do it is that so as you can see, if I write out these numbers, what I will get is that this is, for example, 1 plus 4 plus 9 plus 16 plus all the way up to n squared. And of course, this is no geometric progression, this is no arithmetic progression. There was some way to do this, and that is let me see. Okay, so this thing over here is a little bit, I mean, there is no way to actually find that directly, meaning that, for example, when you write sigma x of I squared, when I goes from 1 to n, that would be the same thing as x of 1 squared plus x of 2 squared, x of 3 squared, and so on and so forth, all the way up to x of n squared. And that is equal to, when you're talking about the first n natural numbers, you're going from 1 squared, 2 squared, 3 squared, all the way to up to n squared. And then this is no, basically, this is not an arithmetic progression. This is not an geometric progression. So, so there is no direct way to evaluate that. But there is a trick that I had actually forgotten, and now that I found it on brilliant.org, that gives the sum of the eighth a raised to the power of n positive natural numbers. And so the way that you can figure that out is that, for example, when you're calculating the sigma of x of I raised to the power 2, of course, when you have sigma, when you have, for example, something like sigma x of I, when I goes from 1 to n, we calculated that as to be, that's a simple arithmetic progression, meaning that if you have x of I raised to the power 1, then you have basically x of 1 plus x of 2 plus x of 3 plus all the way up to x of n. And that's the same thing as 1 plus 2 plus 3 plus all the way up to n. And well, this is an arithmetic progression. As we discussed before, your A is equal to 1, your D is equal to 1, and your N is equal to the number of those numbers is N. You have N terms here. And we said that in the case of an arithmetic progression, S of N is equal to N divided by 2 times 2A plus N minus 1 times D. And then you can calculate this as, for example, S of N is equal to N divided by 2 times 2A, which is 2. N minus 1 is N minus 1, and D is 1, so plus N minus 1. Which is the same thing as N divided by 2 times, for example, 1 plus N, which is N times N plus 1 divided by 2. So that means that if you have sigma x of I, as I goes from 1 to N, that is equal to N times N plus 1 over 2. That is the same thing as, of course, 1 plus 2 plus 3 all the way up to N. For example, if you had 50 numbers, and for example, if you had 50 numbers 1, 2, 3, 4, and all the way up to 50, and if you were to add these together, meaning that if you had 1 plus 2 plus 3 plus all the way up to 50, that would be simply N times N plus 1 times divided by 2, which is, your N is 50 here, so 50 times 51, N plus 1 divided by 2. That's 25, and that's a 1, and 25 times 51 is, for example, 5, 25, 0, 2, and 10. So you have 5, 7, 2, 1275. So the sum of all of these numbers is 1275, for example. The sum of all the first natural numbers from 1 to 50, for example. So that's basically that you can call sigma x of I. That you can call sigma x of I raised to the, for example, raised to the first power. Now, if you're dealing with basically sigma x of I raised to the second power, the formula is going to, the way that you calculate it is going to be a little bit different, because when you have sigma x of I squared, as I goes from 1 to N, that's the same thing as, for example, x of 1 squared plus x of 2 squared plus x of 3 squared plus all the way up to x of N squared. And x of 1 in the case of, for example, natural numbers is 1. Start with 1 and then 1 squared. So 2 squared plus 3 squared plus all the way up to x of N would be N squared. X of N squared would be N squared. So now the problem here is that this is no geometric progression, and this is no arithmetic progression. And you do need to find some way to calculate that. And there is something called a Fallhaber's formula, which is derived below, provides a generalized formula to compute these sums for any value of N, but which is not important right now. But now suppose that you have and this is not a very good proof. Okay, so now I had to basically look for the right proof, because there are many ways of basically doing this, but basically something that I find reasonable enough is basically this one. So you want to consider, let me see. Okay, so I got basically the right place here. So now basically, so we have to basically, we basically calculated sigma. We calculated sigma x of I as, when I goes from 1 to n, as basically as let me see. Number 2, number 1 is, we found this as basically n times n plus 1 divided by 2. So that you already found. Now, if you have basically sigma of x of I squared, if you have sigma x of I squared, I goes from 1 to n, what that means is that you have x of 1 squared plus x of 2 squared plus x of 3 squared plus all the way up to x of n squared. And when we're talking about the set of natural numbers, of course, an x of 1 in the case of natural numbers would be basically 1 squared plus 2 squared plus 3 squared plus all the way up to n squared. And so you can write this thing as s of n in the language of series and sequences. You can write this as s of n is equal to 1 squared plus 2 squared plus 3 squared plus all the way up to n squared. And now there are different ways of doing this, and I forgot to say that you might notice that I had to shave my head in the middle of this video, so that's basically why my head looks different. Otherwise, I cannot have too much hair on my head. Okay, so now what we want to do is basically find the same thing. Basically, we want to find s of n. We want to find s of n, which is basically 1 squared plus 2 squared plus 3 squared plus all the way up to n squared. And in order to find out what that is, we need to find an identity. We need to use an identity. And the identity that we need to use is a minus b whole cube, which is equal to, of course, you know that it's a cube minus b cube minus 3 times a squared b plus 3 times ab squared plus 3 times ab squared. Now in this identity, if I put basically a is equal to k and b is equal to 1, if I put a is equal to k and b is equal to 1, what I will get is basically k minus 1 whole cube is equal to k cube minus, that is b cube, of course, minus 1 cube minus 3 times a squared b, so that's k squared times 1 plus 3 times k times 1 squared. You can write it this way. And so k minus 1 whole cube is equal to k cube minus 1, and that is basically negative 3 times k squared plus 3 times k. So I can write this as 3 times k. Basically, I can write this as, I can keep this on this side of the equation, meaning that I can write k cubed, bring this to the other side of the equation, minus k minus 1 whole cube, and write this equal to, and take all of these terms to the other side of the equation, meaning that I can write this as 3k squared negative 3k plus 1. So k cubed minus k minus 1 cube is equal to 3k squared minus 3k plus 1. K cubed minus k minus 1 cube is equal to 3k squared minus 3k plus 1. Now, in order to use this identity, what I'm going to do is I'm going to put k is equal to, k is equal to 1, 2, 3, and all the way up to n. So when k is equal to 1, for example, then when k is equal to 1, then this equation becomes 1 cube minus 1 minus 1 whole cube is equal to 3 times 1 squared minus 3 times 1 plus 1. When k is equal to 2, then this becomes 2 cube minus 2 minus 1 whole cube is equal to 3 times 2 squared minus 3 times 2 plus 1. When k is equal to 3, your equation becomes 3 cube minus 3 minus 1 whole cube is equal to 3 times 3 squared minus 3 times 3 plus 1. And you can just keep going until basically k is equal to n, and that would be n cubed minus n minus 1 whole cube is equal to 3 times basically n squared minus 3 times n plus 1. Now, if I add all the respective terms of all of these expressions together, what I will get is that this is 1 cube plus 2 cube plus 3 cube plus all the way up to n cube, right? Adding all the respective terms together, adding all the respective terms, what I will get is that 1 cube plus 2 cube plus 3 cube plus all the way up to n cube, which I will write as plus all the way up to n cube, and then I have to subtract from that. So this is 0 cube, which is 0, and this is 1 cube plus 2 cube plus all the way up to n minus 1 cube. So I have to subtract from that basically the 0, so this is 1 cube plus 2 cube plus 3 cube plus all the way up to n minus 1 whole cube. That is equal to basically 3 times 1 cube, 3 times 2 cube, 3 times 3 cube, all the way up to 1 squared, 2 squared, 3 squared, all the way up to 1 squared. So I can write this as 3 times 1 squared plus 2 squared plus 3 squared plus all the way up to n squared minus 3 times 1 plus 2 plus 3 plus all the way up to n, 1 plus 2 plus 3 plus all the way up to n, plus 1 plus 1 plus 1 plus all the way up to n terms, right? Now over here you can see that over here you can see that you have basically 1 cube minus 1 cube, 2 cube minus 2 cube, 3 cube minus 3 cube. So all of these terms will be cancelled out. And of course here you have n minus 1 cube, so here you will get n cube. If you add all of these together, what you will get is basically, for example, 1 cube minus 1 cube plus 2 cube minus 2 cube plus 3 cube minus 3 cube. And you can just keep going, and you will all that you will get is n cube, because I can write this part. If you think about only this part over here, I can write this as 1 cube plus 2 cube plus 3 cube plus all the way up to n minus 1 cube plus n cube, right? And then I can write this as it is, minus 1 cube plus 2 cube plus 3 cube plus all the way up to n minus 1 whole cube. Now you can see that all of these are negative terms, the same terms as these terms, so you can cancel all of these negative terms with all of these positive terms. You will be left with an n cube. So that means that then basically the sum of basically this side of this equation becomes n cube. And then over here you have 1 squared plus 2 squared plus 3 squared plus n squared. You can write that as, for example, 3 times sigma, for example, sigma k squared, as k goes from 1 to n, for example. K goes from 1 to n. Minus 3 times, and over here you have, for example, you can write this as sigma k, as k goes from 1 to n. 1 plus 2 plus 3 plus all the way up to n. And over here you have basically 1 plus 1 plus 1 plus 1 n times, so that's just n. So now my goal was to calculate sigma k cube as k goes from 1 to n. So I keep this over here and write this as, so I can write this as 3 times sigma k squared as k goes from 1 to n is equal to, take all of these to the other side of the equation. So taking this to the other side of the equation, that's positive 3 times sigma k as k goes from 1 to n, and then minus n, or plus n cubed, for example. This is already over there, minus n. And so basically we calculated this to be we said that basically sigma k as k goes from 1 to n is equal to n times n plus 1 divided by 2. So I can write this as 3 times, for example, 3 times this expression over here. 3 times n plus 1 divided by 2 plus n cubed minus n. And then if you simplify this part, and then of course you need to divide, this is 3 times sigma k squared as k goes from 1 to n, and what I want to find is sigma k squared as k goes from 1 to n. So I can write basically sigma k squared as k goes from 1 to n is equal to this expression, this whole expression divided by 3, which is 3n times n plus 1 divided by 2 plus n cubed minus n. And so I can write this as basically, take a basically LCM 2 here, and write this as 3n times n plus 1 plus 3n cubed minus 3n divided by 3. And then if I multiply these two together, what I will get is basically 3n times n plus 1 plus 3n n cubed. This is supposed to be n cubed, right? 3n cubed minus 3 times n divided by 6. So that is sigma k squared as k goes from 1 to n. Exactly what I want to find out. So what I have here is basically this expression. I can simplify it a little bit, meaning that I can write this as, for example, I can write this as 3 times n squared plus 3 times n plus 3 times n cubed minus 3 times n, and I can simplify. There was some 1 somewhere over here. Which became n, of course. Okay. Which became n. Now there is something wrong here. There must be something wrong here. Over here I have n cubed is equal to 3 times sigma k over here, somewhere over here, basically n cubed is equal to 3 times sigma k squared minus 3 times sigma k plus n, right? So this is correct. But this seems to be not correct. There must be some problem over here. Because if I simplify 3n and negative 3n, I will get 3 times n squared times, I can simplify this as 3 times n squared times 1 plus basically n over 6, which will give me basically 2 and 1, so 1 plus n times n squared over 2, which is not the right answer. Now there is something, I have made a mistake over here. I have to go back and see what the mistake was. So let me see what I have done wrong. I know that all the way up to this step there was nothing wrong, but then somehow in these few steps I might have made a mistake, and I know I have made a mistake. So basically my goal is to calculate 3 times, my goal is to calculate sigma k squared as k goes from 1 to n. So I keep it on this side of the equation, so I write it as 3 times basically sigma k squared as k goes from 1 to n, and then take everything to the other side of the equation. For example, this becomes 3 times sigma k as k goes from 1 to n. Okay, and then I have plus n cubed over there, and then I have negative n over there. And I know that, and then I can just simply write here, I can write sigma k squared as k is equal to 1 to n is equal to this whole equation, 3 times sigma k as k is equal to 1 to n plus n cubed minus n and divided by 3. So I can take this whole equation and divide it by 3. Now, what I can do is that I know that basically sigma k, as k goes from 1 to n, is equal to n times n plus 1, n times n plus 1 divided by 2. So I can write this as basically 3 times n plus 1 divided by 2 plus n cubed minus n over 3. And then I can write this as, I can take LCM 2 here. Take LCM 2 here, so this becomes 3n times n plus 1. And then over here I can write plus 2 times n cubed minus 2 times n over 3, which will give me 3 times n plus 1 plus 2 times n cubed minus 2 times n divided by 6. That is sigma k squared, as k goes from 1 to n. Now if I do this, if I simplify this, or I can just simply take an n out, I can just simply take an n out here. You can write this as n times, for example, 3 times n plus 1 plus 2 times n squared minus 2 and divided by 6. That is equal to that. And then this thing over here, I can write it as 3n plus 3 plus 2n squared minus 2. And so this is 2n squared plus 3, and 3 minus 2 is equal to 1, right? And so 2n squared plus 3n plus 1, if you factorize this equation, what you will get is basically, if you multiply these two numbers, 1 and 2, you will get a 2. So 2, you can write it as 1 times 2. Now 1 times 2, so if I write basically 1 times 2, I will get a positive 2, which is basically the product of these two. And if I write 1 plus 2, I will get a positive 3, which is basically this number over here. So I can use positive 1 and positive 2 to factorize this expression. So I write this as 2n squared plus 2n plus n plus 1. And then I can write this as 2n times n plus 1 plus 1 times n plus 1. And then this becomes 2n plus 1 times n plus 1. And this is basically the factorized form of this equation, of this expression, which is equal to n times n plus 1 times 2n plus 1 divided by 6. And that is equal to sigma k squared, as k goes from 1 to n. That is what we were looking for. And what this means is that if you have basically something like 1 squared plus 2 squared plus 3 squared plus all the way up to n squared, that's going to be equal to n times n plus 1 times 2n plus 1 divided by 6. That's the meaning of this. Now there is one more thing that we need to calculate here, and that is because we are going to need that here, and that is basically sigma k cubed, as k goes from 1 to n. Okay, and the procedure is similar. It's not very different. So, and I'm going to go back and write all of these formulas in one place so that we can use them. That's not a problem. So let me make some space here. So then now what we want to calculate now is basically sigma k cube as k goes from 1 to n, meaning that, and the meaning of that is basically 1 cube plus 2 cube plus 3 cube plus all the way up to n cube. We want to find the formula for that. So now in order to do that, what you need to do is consider the identity a, basically a minus b. I think you could do it with a minus b whole raised to the power 4. Let's see if that's possible. If I go with the identity a minus b whole raised to the power 4, that is the same thing as a minus b whole raised to the power 3 times a minus b. Now we said that a minus b whole raised to the power 3 was equal to a cube minus b cube minus 3 times a squared b plus 3 times ab squared times a minus b. But I think we cannot use this actually. If I use a plus b whole raised to the power 4, let me see. If I use a plus b raised to the power 4, you know that a plus b whole raised to the power 3 is equal to a cube plus b cube plus 3 times a squared b plus 3ab squared. And so the same thing, you can write this as a plus b whole cube times a plus b. And if I write this way, I can write this as basically a cube plus b cube plus 3a squared b plus 3ab squared times whole times basically a plus b. And what you will get is basically a raised to the power 4 plus ab cube plus 3a cube b plus 3a squared b squared, and then multiplying b by all of these terms, you will get plus a cube b plus b raised to the power 4 plus 3 times a squared b squared plus 3 times ab cubed, right? Now this is equal to a plus b raised to the power 4. This is equal to a plus b raised to the power 4. Okay, so I think we can actually work with this. So now if I, in this ab cube, a squared b squared, a cube b raised to the power 4, a squared b squared. So we have 3 times a squared b squared. So I can write this as 8 raised to the power 4. And over here I must have some b raised to the power 4 as well, plus b raised to the power 4. And then I have 3 times a cube b, 3 times a cube b, and then I have 3 times ab cube, 3 times ab cube, and then I have 3 times a squared b squared, a squared b squared, and then I have 3 times a squared b squared, 3 times a squared b squared is 6 times a squared b squared, and then I have a cube b, ab cube plus ab cube plus a cube b. Okay, so that's a plus b whole raised to the power 4. You can use this, you can use the binomial theorem to find this, to find out what this is as well. or you can basically also use the Pascal's triangle, but if you do the algebra you will get this thing over here. Now if you set basically A is equal to K over here in this identity, if you set A is equal to K and B is equal to 1, what you will get is that K plus 1 whole raised to the power 4 is equal to K raised to the power 4 plus 1 raised to the power 4 plus 3 times A basically, so that is A basically K, so K cube times 1 plus 3 times K times basically 1 cube plus 6 times K squared times 1 squared plus K times 1 cube plus K times 1 cube plus K cube times 1, K cube times 1, and that would be basically K raised to the power 4 plus 1 plus 3 times K cube plus 3 times K plus basically 6 times K squared plus what is that? That is K plus K cube. So you get basically what you get is K raised to the power 4 plus 3 times, so here you have 3 times K cube plus K cube is 4 times K cube and 6 times K squared, and over here you have 3 times K plus 1. Oh, 3 times K, so that's 4 times K. 4 times K plus 1. So that is K plus 1 raised to the power 4. Okay, I hope that is correct because I want to use it for this theorem. So K plus 1 raised to the power 4 is equal to K raised, or minus K raised to the power 4 is equal to 4 times K cube plus 6 times K squared plus 4K plus 1. That is absolutely correct. Now let's do this part as well, and then we will end this video. Okay, so now in this identity, what we want to do basically, you can put K is equal to 1 to 2 to 3 to n and all the way up to n. So now if you basically putting K is equal to 1, 2, 3 all the way up to n, we will get basically, for example, when K is equal to 1, what we have is basically 1, of course there is something that we need to do first before we do this step, otherwise things will be a little bit unnecessarily difficult. So what I want to do is that I want to write K plus 1, I will write this identity as K plus 1 raised to the power 4, and bring this to the other side of the equation. I write it as K raised to the power 4 is equal to 4 times K raised to the power 3 plus 6 times K raised to the power 2 plus 4 times K plus 1. So K plus 1 whole raised to the power 4 minus K raised to the power 4 plus is equal to 4 times K cube plus 6 times K squared plus 4K plus 1. Now if I putting basically K is equal to 1, 2, 3 and all the way up to n, what I will get is basically, for example, let's suppose that K is equal to 1. I will get 1 plus 1 raised to the power 4 minus basically 1 raised to the power 4, 1 raised to the power 4 1 raised to the power 4 is equal to 4 times 1 raised to the power 3 plus 6 times 1 raised to the power 2 plus 4 times 1 plus 4 times 1 plus 1. If I say that, for example, k is equal to 2, then I can write basically 2 plus 1 raised to the power 4 minus 2 raised to the power 4, right, is equal to 4 times 2 raised to the power 3 plus 6 times 2 raised to the power 2 plus 4 times 2 plus 1. Now, if I say that, for example, k is equal to 3, I will have 3 plus 1 is whole raised to the power 4 minus 3 raised to the power 4 is equal to 4 times basically 3 raised to the power 3 plus 6 times 3 raised to the power 2 plus 4 times 3 plus 1, and I can just keep going all the way up to, for example, k is equal to n, and then there I would get n plus 1 all raised to the power 4 minus basically n raised to the power 4 is equal to 4 times n raised to the power 3 plus 6 times n raised to the power 2 plus 4 times n plus 1. And now if I adding everything, adding the respective terms, what I will get is basically over here what I have is basically 1 plus 1 raised to the power 4. So that's basically 2 raised to the power 4. That's 3 raised to the power 4. That's 4 raised to the power 4 all the way up to n plus 1 raised to the power 4. So I have over here I have basically 2 raised to the power 4 plus 3 raised to the power 4 plus 4 raised to the power 4 plus all the way up to n plus 1 raised to the power 4. And then subtract from that 1 raised to the power 4 plus 2 raised to the power 4 plus 3 raised to the power 4 plus all the way up to n raised to the power 4. That is equal to 4 times 1 cube plus 2 cube plus 3 cube plus 4 cube. That's 1 cube plus 2 cube plus 3 cube plus all the way up to n cube plus 4 times 1, what is that? Plus 4 times 1 plus 2 plus 3 plus again 4 times 1 plus 2 plus 3 plus all the way up to n. And then over here I have 1 plus 1 plus 1 plus 1 all the way up to n terms. So now this part over here I have 2 cube plus 3 cube plus 4 cube, and then this goes all the way up to n minus 1 raised to the power 4. I'm sorry, this is not cube but raised to the power 4. So this is 2 raised to the power 4, 3 raised to the power 4, 4 raised to the power 4, all the way up to n. This is supposed to be n plus 1. Okay. So this is n plus 1 raised to the power 4. So I can write this as, of course I can write this as this part. I can write it as 2 raised to the power 4 plus 3 raised to the power 4 plus 4 raised to the power 4 plus all the way up to before n plus 1 raised to the power 4. I have n raised to the power 4, and then I have n plus 1 raised to the power 4. And then subtract from that basically 1 raised to the power 4 plus 2 raised to the power 4 plus 3 raised to the power 4 plus all the way up to n raised to the power 4. So that means that all of these terms all the way up to n raised to the power 4 are cancelled out together. Meaning that you get 2 raised to the power 4 all the way up to n raised to the power 4. So you get only this term over here, which is negative 1. And then over here you have n plus 1 raised to the power 4. So this side of the equation becomes n plus 1 raised to the power 4 minus 1. And then the other side of the equation becomes basically 1 cube plus 2 cube plus 3 cube plus all the way up to n cube, which I can write as 4 times sigma k cube, as k goes from 1 to n. And then over here I have 1 plus 2 plus 3 all the way up to n. So that means that I can write it as 4 times sigma k, as k goes from 1 to n. And then over here I have 1 plus 1 plus 1 n terms, so that is basically simply n. Meaning that n 1 has been added to itself n times, so that is n. So then let me see if everything is okay so far. Now I think there is something wrong here. Let's see. I think I made a mistake somewhere over here. If I put k is equal to 1, that becomes 1 plus 1 raised to the power 4 minus 1 raised to the power 4. 2 plus 1. So here I get 2 raised to the power 4 plus 3 raised to the power 4 all the way up to n plus 1 raised to the power 4. Maybe they will cancel out. Okay. Maybe they will cancel out. Let's see what happens. So I have okay, so adding both sides together, you get n plus 1 raised to the power 4 minus 1 raised to the power 4 is equal to 4 times 1 cube plus 2 cube plus 3 cube all the way on to 10 cube, n cube. And there is supposed to be a 6 over here, n squared. Which is supposed to be 4 sigma k cube plus 6 times k squared. Where is this k squared? Oh, I have actually forgotten something over here. I'm sorry. So I leave that the other side as it is, and I will have to make some changes here. So you see over here, what I have is the other side of the equation is 4 times 1 cube, 2 cube, 3 cube, all the way up to n cube. So I can write this as 4 times basically sigma k cube. I can write that as 4 times sigma k cube as k goes from 1 to n. Over here I have 6 times 1 squared all the way up to n squared, so I can write it as 6 times sigma k squared as k goes from 1 to n. And then over here I have 4 times 1 plus 2 plus 3 all the way up to n, so that is 4 times sigma k as k goes from 1 to n plus n, which is basically all of these n's together, right? So I can write this whole thing as n plus 1. This is the other side of the equation, which we figured out was n plus 1 raised to the power 4 minus 1 raised to the power 4. And then the other side of the equation becomes this, meaning that 4 times sigma k cube as k goes from 1 to n plus 6 times sigma k squared as k goes from 1 to n plus 4 times sigma k as k goes from 1 to n plus n. That is basically the equation we were looking for. So we have n plus 1 raised to the power 4 minus 1 raised to the power 4 is equal to 4 times this, which is 4 times sigma k cube as k goes from 1 to n, 6 times sigma k squared plus 4 times sigma k plus n. Now, what we are looking for here is basically we're looking for sigma k cube, right, as k goes from 1 to n. Now we calculated sigma k squared to be n times n plus 1. Excuse me. We calculated sigma k squared, this part. We calculated sigma k squared as k goes from 1 to n to be n times n plus 1 times 2n plus 1 divided by 6. We calculated sigma k as k goes from 1 to n as that was basically n times n plus 1 divided by 2. Right? So we already know these two things. We have proved them to ourselves. So I can take this, I can basically rewrite this equation as, okay, so now what I can do is that I can take this formula and write it as, for example, sigma k cube as k goes from 1 to n. So I can write it as 4 times sigma k cube as k goes from 1 to n is equal to basically n plus 1 raised to the power 4 minus 1, and then you have minus 6 times sigma k squared as k goes from 1 to n minus 4 times sigma k as k goes from 1 to n minus n. And then in order to basically, I need to get rid of this 4 from here. So I write that as sigma k cube as k goes from 1 to n is equal to this whole expression divided by 4. So that is n plus 1 raised to the power 4 minus 1 minus 6 times sigma k squared as k goes from 1 to n minus 4 times sigma k as k goes from 1 to n minus n. And then of course you know that basically you know that sigma k as k goes from 1 to n is equal to this thing, which is n times n plus 1 divided by 2 is equal to n times n plus 1 divided by 2. And also you know that sigma k squared as k goes from 1 to n is equal to n times n plus 1 times 2n plus 1 divided by 6. Okay, so now I can substitute these values here, meaning that I can write basically first of all n plus 1 raised to the power 4 minus 1 minus 6 times basically sigma k squared, which is basically this thing over here, n times n plus 1 times 2n plus 1 divided by 6 minus 4 times sigma k, which is basically n times n plus 1 divided by 2 minus n. And you want to divide the whole thing by 4. We don't need this anymore. Now, you know that these two will cancel out. And then 4 divided by 2 is equal to 2. And so you have n plus 1 raised to the power 4 minus 1. And then you have n times n plus 1 times 2, n plus 1 minus 2 times this minus n. And now you just need to simplify things. There is nothing else left. So I can write n plus 1 raised to the power 4 is the same thing as what we started with. So this is basically what you can use in order to simplify that thing. So I think if I use this identity, I can actually use it in order to, so I can write this as now over here I have k plus 1 raised to the power 4 is equal to k raised to the power 4 plus 4 times k cubed plus 6 times k squared plus 4k plus 1. So I can write the same thing over here, but then I have to substitute these k's with n because the variable has changed here. So I have to write basically n raised to the power 4 plus 4 times n cubed plus 6 times n squared plus 4 times n plus 1 minus 1. And then I have negative over here. What we have is basically a negative sign multiplied by this whole thing, which is basically n times n plus 1 times 2n plus 1. So first I multiply these two, I'll get n squared plus n times 2n plus 1. And that is basically 2 times n cubed plus n squared plus 2 times n squared plus n. So you have 2 times n cubed plus n squared plus 2 times n squared plus n, which is 2 times n cubed plus 3 times n squared plus n. So I write it over here, but I have to basically I have to multiply this negative sign by all of these terms. So that is negative 2 times n cubed, negative 3 times n squared, minus n. And then I have basically negative 2 times n plus 1. So negative 2 times n plus 1, n plus 1, which is the same thing as negative 2 times n squared plus n, which is negative 2n squared minus 2n. n squared plus n, so that's negative 2n squared minus 2n. And so I can write this as it is over here, negative 2n squared negative 2n minus n I have over here divided by 4. And if I put all of these together, hopefully we will get the right answer, which is, well, which is the same thing as over here, n raised to the power 4. Now over here I have 4n cubed, I have 4n cubed, negative 2n cubed, that is basically 2n cubed, that is 2n cubed plus 2 times n cubed. And then you have n squared here, n squared, n squared. So 6n squared, this is negative 3, negative 2, negative 5n squared. So 6 negative 5 is equal to plus n squared. So 6n squared, negative 3n squared, negative 2n squared, and then negative, that's positive n squared. And you have 4n minus n, negative 2n minus n. So negative n, negative n, negative 2n, that would be negative 4n. And then you have a positive 4, and they will all cancel out. They will all cancel out. And then you have these two will also cancel out. So 4n, negative n, negative n, negative 2n cancel out. And now all of those terms have been taken care of, divided by 4. And now what you can do is that take the some n squared out, for example, n squared plus 2n plus 1 over 4. And if I factorize this expression, n squared plus 2n plus 1, I will get basically, well, if I write this as I'm not sure if that's possible, but let's see. If I write n squared plus n plus 1, and then n times n plus 1 times 1 plus 1 times n plus 1, that is n plus 1 times n plus 1, which is n plus 1 whole squared. It's not supposed to be that. That's n squared plus 2n plus 1. That's the same thing as n squared times n plus 1 whole squared divided by 4. That's most probably not the right formula. That is actually happens to be the right formula. Okay, so what they have basically written this as basically n times n plus 1 whole raised to the power 2 divided by 4, and that is sigma n cubed as n goes from, or basically sigma, we have written it k cubed, for example. That is sigma k cubed. That is sigma k cubed as k goes from 1 to n. And that is the formula that you have here. So then basically, in short, we got 3 formulas here. And these 3 formulas were, let me show you the 3 formulas. We already write them in 1. So basically, in short, you can say that sigma k, as k goes from 1 to n, is equal to n times n plus 1, n times n plus 1 divided by 2. Number 2, sigma k squared as k goes from 1 to n is equal to n times n plus 1, is equal to n times n plus 1, n times n plus 1 times 2n plus 1 times 2n plus 1 divided by 6. And also sigma k cube as k goes from 1 to n is equal to n times n plus 1 whole raised to the power 2 divided by 4. That is basically all these three formulas that you need, and then of course you can use this extensively in many parts of mathematics, in series, in wherever you go, you're going to need these formulas. I'm going to make a screenshot here and end this video here. I'm going to save it as, for example, sigma formulas number 1, I don't know, on desktop, and save it there. And then in the next video we will talk about the rest of the exercise that we were doing. So I'll see you in the next video.